All sessions I've been. switch.
Yes, so I'm going to be presenting joint work with Jan and Dan. I'm going to start by giving an overview of the goal talk. Hopefully by the end it will be clear. So what we're doing is we're studying key compression functions, key hash functions, where we build them using primitives that we make not function computation. And our goal here is to show that we can count the universality and the universality of this construction as a function of the differential probability of the vector. So we study these key hash functions that take arbitrary length inputs and output fixed length digest under these two use cases, where on the left we have the Carter shoe, and on the right we have protected hash. Here we have so Fk represents our key compression, and Pk prime represents some function that satisfies some the function of security. In the regular part of shoot, we take the message, we compress it into a digest, and then we kind of scramble the digest using nonce and p. And in the protected hash, we take the digest and we. So I'm just going to try and give an intuition. That's why we care about delta universality. So in the case of WCS, well, the attacker can get hold of this blue double M and T, where T is computed as the sum of these two functions. And the goal is that the attacker has to come up with this double M star and star T star, such that the last equation is satisfied. So what we can do is we can look at the difference between these two, the blue and the orange equation. The goal of the attacker is to satisfy this. So we assume there's a verifying goal. So since the blue terms are fixed, the attacker has to come up with these orange terms such that they satisfy this equation. And then it comes with so by playing around and moving the terms a bit, we can get an expression as a function of the output expression function, and bounding the probability of having a fixed output value, difference output value, then it's called the epsilon delta universality of the hash function. And for the protected hash, actually we have a distinguishing scenario where you can see here we're trying to distinguish between a random oracle, and the way we do it is by finding collision at the output of the pressure function. So if we have the same digest, we get and these functions fk in this scenario are usually built in such a way that finding a collision reveals information on the key, so if we can put the key as we want. So then the epsilon universality just bounds the probability of having a free. The way we model our problem is that we introduce this class of key hash function that we call key and hash, which work over a group G and take its input key with max length kappa, and this BS here is the second string over the group of F1. So you can imagine G is like strings of length to the end. Yeah. And then we take strings elements of this group. And the way we treat the key is by doing addition. So we take our message and we add the key to it, and then we do function. So then this leads us to talk about how we define the addition of the key. And we define it like that. We have for any two pairs of strings M and M star, we assume that M is at most as long as M star. And we take the resulting addition as the length of the shortest message, and each character in the string uses the group of the corresponding characters. So here we have a string of length 3 message and a string of length 5 key. This results in a keyed message of length 3, where we have M1 plus K1. And the construction I'm going to talk about in this talk is the parallel construction. We take this small f and we parallelize it so that we can achieve a parallel keyed hash function, parallel keyed and hash function. As you can see here, each function call only depends on the key and their corresponding key and message block characters blocks, and with the digest you can use some of the function. So this is very flexible. You can do it serially or parallel or some hybrid way of doing it, as long as you just take again some of the so as I said at the start, we want to prove bound in terms of differential probability. So I will just give a reminder, but you've probably seen it by now. So we have fixed length permutation f from G to G. We say that input difference A propagates to output difference B to F if this equation is satisfied. And we're interested in knowing how many of such pairs actually satisfy this equation when we fix both A and B. This is what we call the differential probability over F. Here you just have a quick figure that explains what it means to have AB differential. So we would like to define differential probability over parallel F, but classically it's defined over fixed length permutations. So we have to decide how we define an input difference when we have arbitrary length. And this may seem very arbitrary, but the way we define it is that we have the difference between two strings is this pair A lambda, where A is a string of, again, the length of the shortest of the two, which contains the corresponding difference between each character in the string, and lambda represents the length, the difference of length between two strings. So why is this a meaningful definition of a difference? Well, here, if we just look at, so if we apply parallel F on M and then on M star, and we look at the difference between the two, well, assuming that M is at least as long as M star, we can reorganize the equation in such a way that we have the terms in blue here, which are the difference between the corresponding the shared of both strings. And then we have an orange term here, which is just the extra blocks. So what we can see is that we can talk then about the probability of each of these terms having a certain value that eventually we want to sum to delta. And we can see that the blue terms are actually given by a probability mass function, dp of f with AI bi, where AI is just the difference between the I values. And the orange terms, they have a uniform distribution. This is just a random input to a permutation that has this. So that's one of the size of the group. Now we can see then that we can talk about these values of each difference as a discrete stochastic variable with a probability mass function where we fix the input difference between that. And for the orange terms, it is also a stochastic variable with the probability mass function. And then just a quick reminder, when we sum the value of the output of stochastic variable, discrete stochastic variable, then actually we can express this as a new probability mass function that is given by the convolution of the two probability mass functions. And this has an upper bound, which is the resulting probability mass function is bound by the maximum. Just a small intuition, you could replace this term here as max over gx and take it out of the sum. This would sum to 1 and the max. And so what we can realize then is that actually the output difference of parallel f is then stochastic variable with a probability mass function that is the convolution of every stochastic variable in this difference. So then we can define now a differential over parallel f, which has inputs a lambda and output delta, and is given by evaluating this PMF by delta. And then directly from this, we get an open bound of the delta universality, because we can then bound this with any of these PMFs. And since max dp over permutation is at least as good as this, now for the epsilon universality, this gets a little bit complicated, but not that much. Well, we first need to realize that we cannot get a zero output difference with single length, strings of length 1, because it's a permutation and the inputs are different than outputs. So knowing this and knowing that the delta universality bounds the epsilon universality, then we can realize that actually, if we want to find the bound of the universality of parallel f, we need to maximize this term here, which is essentially the convolution of two. So how do we do that? Well, we can then see that this is actually just an inner product of two vectors of t, and inner product of vectors is a very famous bound called the Cauchy-Schwarz inequality, and it says that it is bound by the product of the vectors. And this bound can then be further upper bound by just taking the square, right? Because these are two real values, we take the product of two real values. So then we get this following bound, where actually here we are summing over, we have this delta here, but since we're summing over all t, it doesn't matter, so we can take it out and we get this expression here. But if we want the maximum, then actually value here A1 or A2 doesn't matter as well. So we can just say the universality of parallel F is actually bound by some dp square A T with value A. And actually this bound is tight because if we take our strings of length 2 in such a way that we have a difference that is the inverse of the second difference, then we actually achieve it. Yes, so I would just conclude my talk. So we started with wanting to build a hidden hash function with its security without making assumptions of the permutation. And we saw that we can actually bound the universality only in terms of properties of the permutation, namely for the epsilon universality we get max dp, and for the universality we get sum of dp squares, which is, so max dp is very known everywhere. It's sum of dp squares that's often. Yes, and so in the full paper, we also analyze the serial hidden hash function, and we define these notions of arbitrary length differentials of any kind of hidden hash functions, not necessarily parallel or serial, but any function that just takes key and adds it to the message and does processing. And we kind of these results to reduce Ryan version of so 3 and 4. We see that under some reasonable assumptions, there is a gap between max dp and max dp squared, making it more compelling to use the parallel construction of the serial because there's seemingly no. You don't miss anything you make gain. And that's it. Other than Zoom, yes, we have a paper where we try to build using 4 rounds random, and I'm also interested in permutations that are not round interpretable, where you can actually have a proof of the maximum.
If I'm understanding correctly, I think some of the empathy from the ciphers, it's all hard to figure out exactly what their security is in other ways, but they have nice features that might make it interesting to.
Yes, so this is something that I want to get into, but it's not so clear how this can be useful because, yeah, it's just about generating tags. Maybe some.
Yes, so thank you for the introduction. So this is joint work with Ritan Bauming, Ashmiya, Martin Enning, and Xiaobing Shen. So when we look at a lot of symmetric cryptographic constructions, we see that a lot of them are based on pseudo-random permutations or PRPs, like AES. But a lot of these modes do not make use of the invertibility property that they have. And in a lot of these cases, actually using a pseudo-random function or a PRM is more secure. And the prominent example of this is counter mode. So if we use counter mode with a PRP, then it only offers N of 2 bits security. But if we use a PRM instead, it can offer full N bit security. So what we could try is to design a dedicated PRM, but with little understanding in this, and we are much better with invertible primitives like PRPs. So instead, we could try to design a PRP to PRM conversion method. And the most straightforward way to do this is by simply using a PRP directly as PRM. But this gives only security up to birthday bound. So we can also look at other constructions that give beyond birthday bound security. And one of these is the sum of two permutations. So sum of two permutations takes two independent instances of PRP, gives the same inputs to both of them, and then sums their outputs together using an XOR to get the output of the PRF to Z. And if these permutations are private, so in the case of block cipher, then this achieves 2n-bit security. But in some cases, these permutations are public, so then we move to the pi 0 and pi 1, and the adversary also knows these permutations. And in this case, it gets more complicated, and we have to move to the indifferentiability setting to prove security. So I will now quickly explain indifferentiability setting. So it is a distinguishing game where a distinguisher D tries to distinguish between the real world and the ideal world. But in normal distinguishing game, the distinguisher can often only make construction queries. But in this case, they can also make primitive queries. So in the real world, the primitive are these public permutations pi 0 and pi 1. And the construction is the sum of these two permutations. So the construction depends on the primitive. And in the ideal world, it is a bit different. So what we do know is that we want this construction to look like a random oracle. But a random oracle doesn't have an implementation. So what we have to do instead is that we define a simulated primitive. So we have to define the simulator ourselves, and it should behave like a random permutation, but it should also be consistent with the random oracle. So it has query access to this random oracle to achieve that. And finally, because we consider our permutation, it also has an inverse direction. So we also have, or the distinguisher has access to the inverse of pi 0 and pi 1. So we also have to define an inverse simulator. And all previous works on the, there are three previous works on the indifferentiability of the sum of two permutations. So the first one was in 2010 by Mendel et al. And they showed 2n over 3 bits of security. But in 2015, Mendel and Pernil identified a flaw in this work that invalidated the results, that they were able to reprove the similar bounds. They only lost a logarithmic theorem. And in 2018, Bhattacharya and Nandi improved this result with a new technique to do n bits of security. And all these works use actually the same simulator to some negligible differences. So I will quickly explain that one. So for the fourth simulator, assume that we sequence as 0, and it gets as an input x. So the first thing it will do is query the random oracle on this input x to get the z. And then it will define a set of all its possible outputs. So in principle, it wants any n-bit string as a possible output, but it is a permutation, so it cannot output something it previously outputted. And because this value will also force output of S1, there can also not be collision there, so that gives some more limitations. And because it's some permutations, there's an offset Z there. So from all these possibilities, it's simply uniformly at random draws from this set to get y0, and then it returns this y0. And we also give an inverse simulator. So now the input is y0, and then simulator will randomly draw a fresh x that's not used before. Then it will query the random oracle on this x again to get z. But now it also has to check whether this z is actually possible. Because again, this once we have this c, it will force y1 to be y0 plus z. And that has to be outside of the range of S1. So if it is, we return x. But if it's not, we have to repeat this process and draw new x and try again. And we do this up to the variable L times. So now go to the contributions in our paper. So the first one is that we identify that all these previous works are flawed. So there are quite some flaws in there, so I've made a table to have a bit of that overview. So first we have here the papers, so on 2010, 15, and 18. Security level is supposedly showed, and then 3 different errors, which I will explain later. So the first one I called random range, and that is the flaw present in work 2010 that Menke and Pernil originally identified. And we also show that actually work 2018 contains the same flaw. Next one called sequentiality. So that I actually identified at last crypto and impacts all of these works. And finally, we also have a new one called Fresh Oracle. That impacts 2018. And in addition to this, we also showed an attack on the simulator that everyone uses, using to the power 5 and over 6 queries. So with this simulator, it is impossible to prove more security than this. But we also do have a positive result, and because we are able to sort of fix the sequentiality problem, so then we are able to re-establish this bound of 2015, which we use new technique. So now we'll go over the different errors. So the first one called random range. So when the distinguisher is interacting with permutations or with construction, it also makes primitive queries. For example, in the real world, these are random permutations. So we can look at the ranges of these permutations by 0 and by 1 as R0 and R1. And these are outputs of random permutations. So these R0 and R1 should also be randomly distributed. But that is not the case because this the randomness only holds for forward queries and not for backward ones. Because if we simply make 4 inverse queries using on 4 fixed elements, well then these ranges will this range will always be the set of these 4 elements, and that's definitely not random. And this really is a fundamental problem that you cannot easily fix by some additional steps. So that really invalidates work 2010 and 18. So the next one is sequentiality that I actually explained last crypto, but I have also some additional stuff about it. So what we do here is that we want to modify our distinguisher D to equivalent one D prime to make the analysis easier. So D prime will start by interacting like D. So here, for example, what D does. So in this case, it has an x1 and x2 and makes the corresponding construction queries. And then it will make also the same version as 0, but it will make it on the order of these construction outputs. So if Z1 is smaller than Z2, it will first vary x1, then x2. And if it's the other way around, then it will change the order here. So that's what D does. And then D prime will also make additional verification queries, so also to S1. And then it will output the same decision as D. So it just ignores these extra queries. This one not any important for now. And what we can then see is that this transcript actually contains duplicate information, because these Z1 and Z2 can be derived from this. So be Y1 and Y2 in some order, so you can compute it from this. So to simplify the analysis, we ignore construction queries and only primitive ones. But this ignores that these construction queries that we just ignored can have influence on the next queries. So in this case, we have to query x min first, but this x min depends on Z1 and Z2. So this interaction is not even well defined because we cannot do this. And there's also a similar or a different transformation done that is actually within the same Flaw. So what we do now is that we start again with this interaction with D, but instead of making these construction queries, we immediately make, instead of them, we make these primitive queries. So now our interaction is well defined because we can start with x1, x1, s0, and then s1, and then same with s2 or x2. But in this case, we have actually changed the order of primitive queries, because we should start with x min and then x max, but now we start with x1 and then x2, and they can be different. So again, a positive note is that this transformation and the previous one, that they do work in the weaker sequential indifferentiability setting, because there all the primitive queries have to be made before the construction queries, and then there's actually not really a problem. And all previous works do one of these transformations, so they are all impacted. And what I think is really the core of the problem is that the simulator is treated as a stateless primitive. So a stateless primitive is primitive that can be implemented without states, which means that it has to draw all its randomness at the start. And actually most primitives are stateless: random permutations, random functions, random oracle. You can implement them in a way via lazy sampling, but you can also just for all the randomness at the start and then all the outputs fixed after that. But the simulator is not one of these, because these all contain, let's say, only internal randomness. They only depend on themselves, but the simulator also depends on outputs of the random oracle. So it has this external randomness that it has to query. So its only way to know all its query outputs would be to query the random oracle for all inputs before the interaction, but it's not allowed to do that. So it really is inherently stated. So one important property of stateless primitives is that queries can be reordered. So if you have a fixed x1 and x2, then it does not matter whether we first query the primitive on x1 and then x2, or the other way around. And here we then swap the root, or imagine that the results are swapped. And this property is also used a lot in the symmetric cryptography, the provable side, to simplify a lot of analysis. And here, the same property is assumed for the simulator, and that's, I think, really the core of the Flaw. Because as I said earlier, the simulator is not stateless and inherently really stateful. So does not have the same behavior. So what we did is that we showed that the simulator here does partly has this behavior. So this swapping around is a really strong property, but we are able to show with lots of computations that it does satisfy it to some point, because we're able to show that we can reorder these queries as much as we need up to 2n/3 bits of security. And in combination with the work of 2015, for which the sequentiality was the only problem, we are able to recover that result and then prove that the record indifferentiality with 2n/3 minus logarithm of n bits of security. So now go to the last flaw, which I called crash oracle. So there the flaw is that the value returned from the random oracle is considered to be uniformly as random distributed. Sounds really plausible. I mean, that's what random oracle should do, right? But due to the behavior of the inverse simulator, this is actually not the case. And I will illustrate this with a comparison. So consider that we have a bag of 10 colored M&Ms. And they are uniformly sampled from 5 different colors: the brown, red, yellow, green, and blue. And every M&M has probability of 1/5 being any specific color. So even if the first 3 M&Ms that we draw are all blue, probability that the next one is blue is still 1/5. But now we have a picky eater who doesn't like brown M&Ms. So what they do when they grab an M&M out of the bag and then it's brown, they do not eat it. They take a different one and eat that one instead. So they are not that picky. So even if that other M&M is brown, they will still eat it. And after that, they put original brown M&M back in the bag. And if it's any other M&M, they do eat it. But when we now look at probability that the next M&M is brown, it is a bit different. So they had a probability of 4/5 that it was not brown. And in that case, we don't, there's nothing strange. So the probability is 1/5 that is brown. But the probability was 1/5 that they took the brown M&M. And in that case, they took another one and put it back. So what we have is a bag of 9 M&Ms, of which 8 are of unknown color. So they still have probability of 1/5 being brown. But we also have one M&M that is definitely brown. And so if we compute this, then we see that the probability becomes a little bit more than 1/5 that this M&M is brown. And so a similar issue to this is present in work 2018. So there, of course, they don't have the picky eater, but they do have the picky simulator. And actually, the other works do acknowledge this difference that you between the picky and non-picky simulator, and that is partially responsible for the limited 2/3 bits of security that they prove, because they want to simplify to the non-picky case, and that comes at cost of search term. And we also show with an attack that's actually not possible to ignore this problem if you want to prove more than 3n/4 bits of security. And then we have the final result. I think it's quite interesting. That is the attack on the standard simulator. So recall that the Ford simulator, at some point, it had some set of all possibilities y, and it drew this y0 uniformly from this set, because it looks like we shouldn't have a reason to prefer one value over another. But surprisingly, in the real world, in some cases, it does not behave uniformly over all these cases. So that gives a different behavior of the simulator, and you can actually exploit that using a tag in 2^5n/6 queries. So with this simulator, it's impossible to prove more security than that. So you might be able to fix this with a bias simulator, but that gets very complicated very quickly. And be able to just show 2n/3 bits of security, and this gets really complicated. So I think that more than this, but it'll be quite some time before we are able to achieve that. So now computing. So we saw that established beyond worth about PRP-to-PF conversion methods is the sum of two permutations, and that all the previous works on this indifferentiability are flawed. And we also showed even some limitations for quite a number of different approaches on how to prove it. But we also do have a positive result because we're able to reestablish regular indifferentiability with 2n over 3 minus the logarithmic of n. So that's the end of the talk. Thank you for your attention.
Questions from the audience?
Just to check, is indistinguishability setting?
No. Yes. Yeah, I think mostly the indifferentiability setting that it's, I guess, very complicated. Also, I think more complicated than we expected to really take care of a lot of details. Yeah,
It is valid. I've seen those tricks in other differentiability places. With the other places,
yeah.
from the beginning,
Yeah, so last year I also looked at some works and they are indeed more common, but it's also quite some work to look at one complicated proof and to see is that error in present, because sometimes a bit hidden.
it's not sure, at least
I think that there is more to it. Yes.
very quick related question. So, do you have a better simulator that you can actually get?
I was thinking about above 2n over 3. The current simulator, I think, would be able to achieve that, but
Not
no.
As you saying already, we believe that the currency that we can possibly have 5.6.
Yes.
But to prove that, I think this is
Yeah. Think about the. Because I tried to see how the simulator would like circumvent the attack, but of course you don't want to use specific properties of the attack. But I think you are able to do that, but you have to introduce biases and how much exactly is not clear to me, and it's really complicated.
Questions? Thank you, Speaker Lane. And we have 10 minutes. Switching break.